Okay, so looking at exponential growth and decay, this is very similar to what we looked at last year. When we're looking at growth, a lot of the times we're talking about money, so like savings account, RRSPs, buying a car, something like that. There's also the classic population, bacteria growth. Decay, it's typically looking at like chemicals, so like half-lives and things like that, carbon dating. Again, depreciation of a vehicle. Okay, we're always considering like an exponential growth, which means that we're multiplying by the same number each year or each decay period or growth period. So the example here, we're growing by 5% each year. We're changing the percent to a decimal and then multiplying by 1.05 from the original value. Okay, it's just showing that we can put it into exponential form. So a vase was purchased in 1990 at $8,000. What was it worth in the year 2000? What's it going to be worth in the year 2030? So all we're going to do is we're growing by 6% each year. So if we're growing by 6% each year, we're going to have our final amount is going to be worth our initial value times 1.06. And then our t value, or our exponent, is just the number of years. In this case, we've grown for 10 years. From the year 2000 to the year 1990, it's going to be a 10-year difference. So we got 1.06 to the exponent 10. And then we're going to times that value by 8,000. And we get $14,326.78. Now, if you look at up to the year 2030, you might expect it to be 4 times bigger because it's another 30 years. That's like 40 years in total. So if we just look at this, we're going to have A equals, we've got 8,000 again, because that's our starting value. I guess technically you could have started here and then just done 30 years, but it's always better to start at the beginning and then kind of go backwards, just in case you made a mistake. So we're going to have 1.06 to the exponent 40, and then times that value by 8,000. And you're going to notice here, we've got a much bigger number. It's not just 4 times as big. It is, well, it's close to just over 10 times as large. Okay, and then we would put therefore statements for this, stating what our answers were. So something like that. Our standard form is always our final amount is equal to our initial amount. We've got our growth or decay factor, and then our time. And our time is sometimes going to be given as something like this, like x over d, where x is the time allotted and d is the time for that period to happen. So like a half-life. If it says a half-life every 2 years, then d is going to be equal to 2, and x would be in years. We're looking at this, so the world population doubles every 35 years. So that's told us how long a growth period happens. If we've got 6 billion people, so we'll just use population equals 6. We're just going to talk in billions. And we're doubling, so we're going to have 2. And then we need to have every 30 years. Let's just make the equation. So we'd have P at T, and then it's going to be T over 35. Okay, because it takes 35 years for this to happen. We're now looking from 2050 down to 1999. So that's going to be 51 years. We're going to have 6 times 2 and then 51 over 35. Now, this is a part where you want to be able to use your calculator well. I always like to use brackets with my exponents. You can obviously divide this out first if you want to. But when we're doing this, we're going to get 16 billion or 16.47 billion. Okay, now if we think about that, it's doubled, and then people will be like, well, why is it more than double? Shouldn't it be closer to triple? Well, remember, it's doubled and then it's almost doubled again. So we've gone to 12 and then we've gone a little bit bigger. So we're at 16. Okay. And now when will the population equal 24 billion? Now all we're going to do, 24 equals 6. And then we've got our exponent. We're going to divide the 6 over first. So we're going to get 4 equals 2 to the t over 35. Now you could use logarithms here, or you could just see that this is 2 to the 2 equals 2 to the t over 35. Now we know that 2 equals t over 35, and t equals 70. Okay, you could use logarithms. You're going to get the answer. You just got to make sure that you're careful with it. This one's nice and easy because 2 to the 2 is easily 4. So therefore 70 years, and up here, therefore 16.47 billion. Okay, we then got a population one. This is very, very similar to what we were just doing. The population was something in one year, something else in another. So determine an expression to find it in t years after 1980. Well, we know that we've gone from 24,000 in 1980. So that's our start. We know we got to 29,000 10 years later. So we need to find our growth value because we know that we've gone for 10 years. So this one is a little bit more confusing because we're starting with our final population. It's equal to our initial. We've got our growth to our time. So we're going to do 29,000 divided by 24,000. Okay, we're going to get 1.208 and a whole bunch of threes. And now a lot of people forget to get rid of that g to the 10. All I have to do is take the 10th root of the other side. So I'm going to take the 10th root of the other side, and we're going to get our g value is 1.02. So this is our growth value. That's a percent as a decimal. So then therefore that's going to change to 2%. Okay, remember our growth value, if it's a percentage, we always do 1 plus whatever the percent is as a decimal. So what will the population be in 2020? All we're going to do is P at T. I'll write out the equation here. It was 24,000. We had 1.02. And then the T in this case, we're going to do 2020 minus 1980. So we're going to have P at 40. Equals 24,000. And then we've got 1.02 to the 40. Okay, because it's a 40-year difference. I'm going to use 1.02. I'm not going to use the big long decimal. I'm just using what we have here. So then we're going to times it by 24,000. And you're going to get 52,992 people, 0.9. Some people will tell you need to round down always because you can't have a decimal of a person. If you rounded either way, I wouldn't mark it wrong. I'm more concerned about the process. So here we've got 52,992 people. Okay. Looking at the next one, we've got a car depreciates by 15% per year. If you buy the car, what's the cost going to be, or what's the price going to be in X amount of years? So depreciation, if we're going down, we're starting at 100%, we're going down by 15. So that's going to be 85%. Okay, now 85% as a decimal, it's going to be 0.85. So that's our growth factor. Okay, we've got our cost or our price or however you want to label it. It's 15,000 times 0.85 to the T. After 3 years, our cost is going to be 15,000 times 0.85 to the 3. So we've got 0.85 to the exponent 3 times 15,000. It's going to be about 60% of what you bought it for. Now, when we're doing this, we always have to round it to money, so 2 decimals. So therefore, we've got that. After 10 years, we would do the exact same thing here. So we're going to have C equals 15,000 times 0.85 to the 10. So we would have 0.85 to the exponent 10 times 15,000. And we're going to be down to $2,953.12. Again, you got your therefore statement. Last one, we've got a half-life. A half-life just means that our growth factor is 0.5 or 1 over 2. So if a half-life is this many years, it's going to make our exponent t over that value. So if we have 10 milligrams to start, we want to do our amount is going to be equal to 10 times a half, and then t over 1620. So we would have 10, and I'm going to change this to 0.5. It's just easier to put it in your calculator. Again, you want to be pretty good at using your exponents in your calculator to do this. So we're going to have 0.5 to the exponent. I, again, like to use my brackets when I'm doing this. And you're going to get, this is going to be approximately 9.79 milligrams. Okay, therefore, we've got that. Even here, after 500 years, which makes sense because we have to get this many years to get half of it. So 5 milligrams would be after 1620. We don't need to do t. It's the same equation here. So we're going to have 500, which is going to be, I'm going to just change that real quick. Still actually not going to get us down to a half. We've got 500 over 1620, which is going to be 0.5 to the exponent. Again, I'm going to use brackets. 500 divided by 1620. I'm closing my brackets, and then I'm timesing it by 10. Still not even close to half, which makes sense because we're not even close to the half-life. Okay, we're only about a third of the way there. So then, again, that's in milligrams. So therefore, you have this many milligrams left. Okay, and that is that. It's pretty much a review of grade